Okay, let's get started. We do have a good crowd over here. We have like 53 people. Thank you all for coming on a Friday morning. It's not easy waking up at 8 a.m. I know my struggles of that. Um, Today we're going to talk about CNN basics. And before we start our talk, I need to give out a disclaimer, both on behalf of me and Mansi. This topic you won't be seeing until the next Wednesday, if I'm not wrong. Is that right, Mansi?
Yes, it will be taught on Wednesday.
So you have to bear with us today. We are not trying to fill in Viksha's shoes, but we want to give you an overview so that you get started with homework 2P2, which will be released on Sunday. Now, what have we covered? We have covered what's a perceptron. We have designed a simple MLP structure, and I hope you're working on your homework 2P2. Homework 1P2. You have seen how patterns can be detected using this MLP structure. We have seen backpropagation, how the gradient flows, and we have also learned how weights and biases gets updated in this process of gradient flow. So what's the agenda for today? We'll talk about why a simple MLP structure cannot work for more generalizable deep learning tasks, like suppose image classification. What are scanning MLPs? What is a CNN? What are the different terminologies that are associated with CNN, like filter, channels, try, we'll talk about the whole process of convolution. We'll talk about the forward function of a CNN, which is basically how we have the inputs and we multiply the weights and we get the output. We'll talk about downsampling techniques. Like these are some of the basic like network architecture related stuff that we need to think about when we are employing a CNN. And we'll also give a brief overview of backpropagation. This is a huge topic. Viksha has a separate lecture altogether to talk about backpropagation, but I'll do my best to like just introduce it so that you know what exactly this is. And if you have come across anything or any article, it will just remind you of like what we talked about. Okay, so here's the thing. You know that your MLP can scan a pattern given whatever input you have. And what happens exactly is that MLP is very sensitive to a location. So suppose you have an audio recording and you're playing it and you hear the word Harry Potter. Now this word only comes in the 5th second of your audio recording or your utterance. If you have all these samples which have Harry Potter in the 5th second and you try to train your network, the network won't be able to detect Harry Potter if it comes on the 7th second or the 10th second. So the pattern is fixed to like very sensitive to a location when the MLP is trying to detect it. And same thing with memes, because we like memes so much in this class. Suppose you have this meme of a dog and you want to go ahead and detect in the next meme where if there's a dog or not. So you train the network with a set of images which has dog suppose on the left side. But will your MLP be able to scan? Will your MLP be able to recognize a dog if it comes on the right side? Basically, no. So this process of having your pattern being recognized, no matter where is it, like agnostic to location, is something that we want to develop in our network, and that process is called shift invariance. And a CNN is basically, or convolutional neural network is basically a shift invariant network. Okay, this is just weird. Okay, so how do you detect patterns in shift invariance format? What you basically have to do is like you have to take windows of your input, you have to build a MLP for that area, you try to scan it, and your MLP slides over. Or you can have like different MLPs that are scanning different input, like different input windows, and then you do a max of that output that you get. Because if there's a specific pattern that you're trying to recognize in a specific area, that location will have like, you can say like higher emphasis. And we want to do a OR function where you go through all the MLPs that have scanned different windows of the input, and you want to figure out what is the max of that whole process. And that's basically what a CNN network comprises of. So we can do a 1D scan for sound, because sound is basically a 1D data structure which has like, it has like frequencies. So it's based on time. So you can just scan through the audio clip and like figure out where the word Harry Potter or any word that you're trying to detect appears. if you're doing a scan for images, you have to make sure that you're scanning through the width and also through the height. So it, like suppose in this picture, we have the scan which is going through the picture of the dog, and it's going from left to right. But also imagine if we wanted to extend this picture to a larger size, the MLP had to scan it also through the height of the picture. So that's basically what scanning MLPs are. So we talked about scanning MLPs, and this is something that you will see on the Wednesday lecture. This is basically picked out from Bhiksha's slides. So you have this huge audio recording, right? And which is like indicated in red, blue, red, and purple. And you have different windows of your input that you want to check and see if you can recognize a certain pattern that you're interested in. So you build an MLP, you recognize, you try to scan the first window. Then you build a second MLP, you try to scan the second window, and so on. So it goes through the entire length of the audio input that you are trying to consider. And then you do a max function like we talked earlier, because you want to figure out if this MLP scanned a pattern or did this MLP scan a pattern. So like which MLP was actually able to recognize it. So you do this, and you do this for the entire length of the input that you're trying to provide, or even like width if you have an image. So that's basically your CNN, and that's basically a very raw and very simplistic way of thinking about like what exactly your CNN is doing. So before we start diving into like the exact process of like a forward function in CNN, let's talk about what exactly we want to detect and how the input looks like. So images, we know like images are basically, and I guess like you came across this for your homework 0, if I'm not wrong, you had to pad and you had like different channels. So images are basically, or colorful images are basically comprised of 3 channels. There's red, there's green, there's blue, as you can see in the picture over here. And each of these channels are a set of pixel values. So like in this particular example, we have 4 pixel values. That's the width of the image, and also the height has 4. In most cases, and also in your homework, we will always talk about like square images, or you can like also employ different PyTorch libraries to make sure the images are in a square format. So if it's a colorful image, it will have 3 channels. If it's a BNW image or black and white image, it will have 2 channels. You would also see higher dimensional channels in your input. So yeah, so that's the introduction to what exactly images are. Now, we want to talk about how this entire convolution process works, okay? So let's look at the GIF above. What we have is the blue colored square, which is basically a set of pixels. That's your input. And then we have this small green square, which we will call as filter, or you can say it's a kernel. A kernel is like a more, is a better terminology. And a kernel could just be a set of weights. And what we want to do over here is basically move this kernel, like the way it's moving over the image, and try to detect pattern. And why we want to assign a greater emphasis on the area where you will have, like you want to detect the pattern at, right? So basically, if your pattern is suppose in the first 6 pixels of your image, you will have some pixel values, and you will have a constant set of weights which is scanning the entire area. And because it will scan through the first few pixels and recognize that there is like a heavier weight in that, ultimately when you sum and you get the output, you will figure out like this is where the pattern was. And to get a better understanding of it, we'll just go through an example where we see how the weights are multiplied with the input pixels. But for now, let's talk about the basic terminologies. So we have filter, which is basically a set of weights, and that can be applied to an image, right? Like the way we're applying it over here. Then we have stride, and a stride is basically the amount by which the filter moves. So suppose here the filter is actually moving by 1 column, so we have a stride of 1. You could also use stride of 2, 3, etc. And that actually is a hyperparameter for you, and you would be using different strides to train your CNN based network in P2. Input channels, like we talked about, for a colorful image, you will have 3 channels. You could also see more channels. So that's your input channel. And the output channels is basically the number of filters applied. Again, like hear about this, but we're going to talk about how the number of channels are decided, or number of output channels are decided in the next slides. Oh, padding. So suppose you have this, you have the kernel and you have the image, but sometimes you want to move your kernel with a greater stride. So instead of 1, if we do a stride of 2 or a stride of 3, the kernel will have no output towards like the last set of scanning, because your input size is basically limited, right? So in that case, if you have a filter size, and if you have a larger, or if you have a different size image, and you want to try out different striding techniques, you will have to pad your image on all the sides. And if it's like a audio clip, you would pad it only in like that one dimension that you're trying to scan in. So that's padding for you. And output size. So this is a formula that you should remember, because you need to determine what and how exactly the output looks like. And that highly depends on your padding, your kernel size, or this and the stride. So basically width and height, or width or height, is basically the input dimension that you have over here. Your kernel size is the size of the filter. So here it's 3. Yeah, I know, I recognize this, that the GIF is showing 2, but it's scanning like 3 pixels in length and breadth. So we'll just assume that it's the kernel size is 3 for now. And then you have 2 multiplied by padding. And this padding can be 0 if you do not really provide any padding over here. And stride is something again that you decide. And this is what your output size formula would look like. So basically now let's look at what exactly is happening in a forward function of a CNN. So you have these weights, right, which is your kernel. So your kernel moves through the entire image, and it tries to do a sum product of the values that it's getting. So here the kernel, you have these 1s and 0s as your pixel values in your image, which is like the green part. And then you have this yellow kernel or filter, which is moving along the length and the breadth, and it's trying to compute something. And the final computations are presented in this pink box over here. So let's go step by step. So we have to apply a filter, and the filter has weights of like 101, 010, 101. Okay. So what happens is this filter will move along the length and the breadth of the image. It will try to do a sum product. And suppose we want to see how it's getting the first output, like the output at 0, 0 location of the main output matrix. So what it does is basically take this 1, it multiplies it with the 1 in the weights vector or the weights matrix or the kernel that's present. And then it takes, let it move back. And like it takes like 0, and then it multiply it with a 0, because we have a 0 over here. And then it has 1 multiplied by 1. It has 0 multiplied by 0 again. So this entire thing is basically a sum product, and you finally get 4. In the same way, when you like convolve the filter for the next output, you will get 3. That's basically the forward function of your CNN. Now, we are talking in terms of weights, right? Because that's your kernel. What happens, because you also want to add a set of biases to these. And that's basically added to the final output over here. You don't really convolve a set of biases like the way we do for weights. You basically have like a set of biases that you add to the output size. Okay, so that was a 2D picture for you. Now let's imagine what exactly is happening in 3D. So you have these 3 channels which represent your images, and you will also have a similar kernel which has the same sort of 3 channels, that needs to convolve over the input, right? So it will again go through the input size, and it's exactly like a 2D function, but basically we are now trying to visualize in 3D and see what exactly is happening. The kernel will move over the image, it will try to do a sum product, and you will get the output, and then you add biases. So this is what a 3D structure looks like, but let's talk about if you have multiple filters. What happens is, so here are your different filters. This is from one of the blog posts that I was referring to. So they have called these as weights, but these are basically your filters. And what it does is it will convolve through the image, and you have 4 such filters, right? And because you have 4 filters, in your final output, you will have 4 channels. Now, basically, you will see problems in which you have a defined number of channels, and you have to figure out like what is the number of filters that were applied. So the basic formula is the number of filters is equal to the number of output channels. So just remember that. I'll just try to like modify the slides and include that over here so that you guys remember it. So that's it. That's your 3D convolutional picture with the different number of filters that you have to do the convolution, and you get like the number of filters equals to the number of output channels. Okay, so let's talk about padding, and this is how padding looks like. You had a 4x4 image, and you had a 2x2 filter or kernel. You wanted to move this kernel along the length and along the width of the image, but suppose you want to do it with some extra stride, which is not 1. What happens is this filter will first go through this part, and then it will move by a stride 1 if we have a stride 1, and then it will move by again by a stride 1. So in that way, if it has a stride 1, it will cover the entire length of this image. But if it's more than stride 1, it will first go through this part. Suppose it has a stride 3. It will first go to the first 4 input pixels, but next it will try to jump off because it has 3, and it will try to detect something over here. And basically that is beyond the dimension of the input. And that's not what we want, because we want the kernel size to go through the entire length of input, right? Otherwise your code will start throwing an error. So that's why we pad the input, and we pad it in all directions, so that because we're talking about like a square input and a square filter, it should be padded in like both directions. So again, because now the filter is trying to convolve over. Convolving is basically a process in which you're like scanning the input. So because you're convolving over the entire length of the input, you will again do a sum product, and you will get these values, which should be your output. Now, as the number of paddings increase, your output size would basically increase. And that's why you should go back and refer to the formula that we talked about in the previous slides and see what your output size could be. Okay, so let's talk about downsampling techniques. And pooling can be basically considered like a layer that you apply to your network architecture. And it basically is employed to reduce the number of parameters that you create in your convolutional process. So the pooling, there are 3 main types of pooling basically. And before we go into that, imagine this is the final output that you get after the convolutional process. And you want to downsample it basically, or you want to reduce the number of parameters for reducing like the complexity of the code that you're trying to create. And you want to just pick up certain parameters within it. So you apply a pooling layer after your CNN layer, and you can either do max pooling. Now what happens is max pooling. Basically, you again have like a same filter size or a same kernel sort of thing, which convolves over right now the output of the convolutional process that you get. And it tries only to pick up the maximum value that you had in your sum product. So basically, when you're convolving this and you have like a 2x2 filter size, let's imagine it's a filter size again, you want to see like what is the maximum value here. So you get 20. For the next set, again, you move the filter by stride of 2, and you see what is the max value over here. So again, that's 30. And similarly, it's same for the other process. A main pooling is very similar to this, but instead of doing a max, you will see and you will figure out what was the min value over here. And I guess like that's 8 for you, right? Because I have this weird zoom bar right on top of the image, so I can't really confirm if, yeah, it's 8. So, and then if you move the filter over here, you will actually choose 0, which appears twice, but it doesn't matter. It's a min pooling case, and here you will choose 34. So average pooling, it's a similar process. Okay, yeah. In this, we have like 2x2 pooling with a stride of 2. Again, we are moving the final pooling filter on the output, and you will try to figure out what is the average of the first few inputs that you take in, which is basically from the output matrix right now. So you do you do a average over the inputs and figure out what exactly that is, and that's your downsampled value. So that's pooling for you. Now let's talk a bit about backpropagation. Okay, before I do that, Mansi, how are we doing on time? Do we have time?
Yeah, we have time. Go ahead.
Right. So this is a very convoluted process, and no pun intended over here. Um, so we have seen how we talk about inputs. We saw how we do a forward function by multiplying the weights to the inputs, and how we get the output function, the output matrix. But what happens is when you want to update these weights and biases, you have to remember first, your filter will contribute to every output that you get. Like suppose over here, the same filter is moving through the entire image from left to right and from top to bottom. So even though each input pixel is not contributing to each of the output, the filter would. So that is what we show over here. It's again a partial differential equation like we have seen in the previous backprop case. And what you do is basically you have a loss function. You try to figure out the value of dl by, this is d by oo is basically the loss with respect to the output at one of the input side of the one of the output matrix, which is like at 0. And similarly, this was like the loss at the output at 0, 1, and like so on. And you want to use these values to update your filter sizes. And your F00 is basically your weights that you see in your filter. So before we do that, the problem with convolutional backpropagation is basically if you employ padding and if you employ strides, a lot of zeros, and there would be gaps in between, right? Because when you do a striding process of greater than 1, you are basically skipping one of the columns and you're trying to move on to the next column to do the forward process. In that way, some of your inputs will again not contribute to the output, and you have to account for that. And that's what makes the process a little more complex than what we have seen earlier. And you have to make sure that your the final output matrix that you have and the final DL by like the loss calculation that you do with respect to the outputs, that needs to be spread out. Now we'll skip to like 2 slides ahead and see what do I mean. So if you have like a stride of greater than 1, you will be having zeros that needs to like, we need to put in these zeros between the output, between the loss derivatives with respect to the output, so that we have like a greater filter. Now imagine like this becomes a filter and we have to convolve this over the input size again to get the updated weights and biases. But for this process, I would not try to like waste time and try to explain it because this involves a lot of math and we haven't gone through basic math over here. Diksha would be covering this in class and like talk to you about like how exactly these zeros are included. But if any one of you wants to think about this before Diksha starts, I'm happy to do it in my Monday OH, sitting with you and like walking through all the equations that we have. But basically for now, just imagine, just because you have some stride greater than 1, and that does not really matter when you have stride of 1. If you have a stride greater than 1, that's when the problem arises and you want to feed in these zeros with the, in the output matrix that you have, or the DL by dy values, so that when you use that as a filter to convolve over the image and get the updated weights and biases, you will account for it correctly and account for that stride which was included in the forward function correctly. Okay, so this was like just to give you a brief overview of like what exactly happens in the backprop process. So we saw what a forward function looks like, right? So we have these images, we have these filters, we have this one filter, sorry, which convolves over the entire length of image, and it tries to do a sum product. So this is basically all your outputs, and we are doing that sum product to figure out like what exactly these outputs are. And when you want to loss with respect to any one of those filter values, because the filter values remains the same for all the outputs that you generate. Like we said earlier, it's not the input pixels may not contribute to all outputs over here, but the input the filter size would definitely do that. So suppose we want to calculate this D loss by D of any of the filters, or one of the weights of the filters. You basically again do a sum of dl by dy, which is your loss with respect to the output, and here we apply chain rule again. And we use dy upon the d filter, and that's how, like, if you want to expand upon this, this is how your dl by df00, which is like the first weight in your filter size, would look like. So this is like a very brief overview of like what back propagation is, and like what exactly is doing, and why we need striding, and why we need to include all those zeros. But this was just to give you a brief overview. Don't stress about it. You won't be doing the math right now, because we would recommend you starting with homework 2P2 first, and then as and when Diksha starts teaching more in class, you can go ahead and start with homework 2P1. But that's it. That's from my side. And before I forget and I leave the stage to Mansi, and she gets to start talking about all the code, don't forget to start your homework 1, P1 and P2. And I have a famous quote over here, and inspired by Kushal's, sorry, let's go back. Kushal's auctioning process of OH. I would like to auction a 30-minute OH to anyone who could figure out where this quote is inspired from. And you could write that on the chat, and the TAs will monitor and tell me. So that was the basic theory of CNNs for you. Mansi will go ahead and cover what exactly you do in PyTorch and how can you get started with homework 2P2.
Thanks, Rashmi. So in this part, we are going to talk about how we are going to use convolutions in PyTorch, and that will be particularly useful for your part 2s. So going ahead, these are some of the reads that you can do. Torch or end documentation will be very useful once you start with your homework 2 part 2, because you know every man page that you have to read, you will be just on this page. So just go ahead and read them. These are some of the libraries that we are going to be importing and using in today's sheet. So starting with the sheet, these are just the sample inputs that we have made. Autograd variable generally you do not need to use, but it just takes care of the fact that the returns are not repeated tensors. And torch.random will simply return you random values from a normal distribution of whatever size we have specified. Here we have tried to create a single 32 cross 32 RGB image, 3 for that RGB thing. And this is a simple signal that we have tried to create where the 40 dimensions are for the 100 time steps. So just like sample inputs over here, coming on to how you are going to use conv2D in PyTorch. So Torch takes care of everything via a library. Here you have a direct library which you can use, which is torch.nm.conv2d. And since we talked about all the hyperparameters in the first part where Rashmi explained the input channels, output channels, kernel size, stride and padding, there's everything available for you and you just need to put in the parameters. Now, how are you going to decide the parameters? It's quite up to you. Input channels will mostly be fixed for the first layer because that will be depending on your data that you would be getting from us. But output channels are something which you might be experimenting for the middle layers. Kernel size, stride, padding, everything is all on trial and error basis. But you just specify it and you get a one conv2D layer. If you have to use the conv2D layer, then you just pass it whatever data you have and like just for simple experimentation, you get it. Now, in the last section where Rashmi talked about, we learned a simple formula. So let's do some maths over here and try to get the eureka moment. So we had the 32 cross 32 image over here. So your input features were 32. Now here is your kernel size 5 and your padding 2. So if you see this, then 32 minus 5 plus 2 into padding by stride plus 1 will get you 32 back. So just do some maths and you would be seeing that, you know, whatever input size you had provided to this convolutional 2D layer, and based on whatever parameters you had specified, you are actually getting the same number. So this is quite helpful in debugging whenever you are in the middle of, let's say, in your model, and you want to check where what is going on. So yeah, and talking about padding over here, if we have not specified stride, it's the by default which conv2d takes is your stride of 1. So here we have like, if we have padding 0, we are downsampling it. So you can see again, do the same maths on 32. You see that it will be 32 minus 7. So just the same maths again, like we don't have a padding here. Here we have like a padding of 1, we have a padding of 2. So the moment you keep on increasing the padding, you will reach a position depending on the kernel size and padding where you can reach the same size of your image. So that's why these parameters are like quite helpful when you would be knowing what to put when. You can put padding, like different padding in different directions. You can specify it, like here you can see we got a padding of, when we put 0, 3, we got a different output. So yeah, it's and you have like different types of padding and just not 0 padding, because here if you put just simply padding 3, conv2d puts like a default 0 padding. But if you want to put like different types of padding, then you can read more about it. There are various types of padding, like reflection, where it will take like just the pixels wherever it has to pad to in the end and put it. 0, we are talking about it. Constant, you can specify a number that you want to pad with. So there are different types of paddings, and they are available in the Torch library. You can experiment with them. Yeah, coming on to convolutional layers now. So basically here we made one single layer, which was our convolutional layer. But generally when you are writing your part 2, you would be having many more layers. You would be making like, we talked about mean pooling. So here is like the function, the average pooling for it. And you can make ReLU layer, you will make several others layer, whatever layers you want to make. This all will be basically in your, maybe in your basic block or in your module function. There'll be various layers, and ultimately you will be passing them through sequential, stack all the layers up and pass your input through it. You will get the same size. Now, the thing which you need to observe is that after you pass like your first conv2d layer here, you got the 32 cross 32 image. And here, if you see, you passed it through the average pool and your kernel size was 32. Since it was 32, you got like a 1 cross 1 image. So all these numbers, whatever you would be getting in the middle of your images, in your layers, you can work the maths out. Like, so just be careful about, it will help you debugging that whether I'm on the right track, whether I'm doing right and or not in the middle of your part 2. So this section is basically to let you know that conv2d and other similar functions exist in torch.nn.functional also. You would not be using it is just a good to know factor, where the problem is that why we don't use it is because you have to make all your parameters on your own. Like here, you don't have anything by default given as input channel, output channel. You have to make your own. You have to specify 20s, like the number of output channels. These are the 3 dimensions of the filters that we want. This is a 5x5 filter, and then pass it on. So it's a little cumbersome process. Torch.nn.directly conv2d is more simplified rather than just using functional. But yeah, just a good to know. Coming on to normalization and dropout, batch norm and dropout is something which you mostly would be needing in this homework. So if you would be needing it, and I think many of you have used some of it in the first homework also. So if you would be needing this, you can put this entire thing in your basic block or in your simple layers module function. You get like conv2d here. you pass it on to whatever input image you had, and then you again pass it on to batch norm, then the ReLU and the dropout. So you can just simply stack all the layers up like this and print it. So just for the examples, and you can calculate how you are going to get the dimensions out. Dropout 0.5 is basically the probability with which you would be dropping the kernels. And you can read more about what this probability does, whether when you should increase it, when you should decrease it, depending on how you see overfitting in your model. So yeah, that's one part. Coming on to downsampling and upsampling, we talked about this in the first half also. So downsampling is the same thing with the same concept that Rashmi explained. There are various types of downsampling techniques. You can use a max pool, a min pool, or a mean pool, basically, that is average pool. So here we had like the kernel sizes too. So remember the input image was of 32 cross 32. And since you passed like a kernel size of 2, you got 16 cross 16. So yes, what stride you would be passing is again like on a trial and error basis. Generally, you would, once you start with a number, like let's say 1 or 2 in the beginning, and then you start getting the results, you will get a hang of like, okay, what I should be using. So yeah, that's one technique. The other technique, since in convolution, if you don't specify like the padding enough, but you stride a lot. By striding, I mean you use your filter to jump more steps rather than the size of the image that you have, you would be getting a smaller sized image. Again, working out on the same maths, if you have 32 and the stride is 2, kernel size is 5 with padding 2, you would get a 16 cross 16 image and not a 32 cross 32 image. So you need to decide whether you need to pad more or you need to pad less. Like towards the uh, limited or the end layers in your model, where you, let's say you want to get like a smaller output in the end, because let's say you have to pass it to the softmax or the linear towards the end to get some designated 16 cross 16 or 32 cross 32 image for a larger input image, you would need less padding. But in the beginning, when you are if you want to upsample the image, if you are working, let's say, on a tiny ImageNet, and you have to extract information out of it, you might want to upsample the image. So these are some upsampling and downsampling techniques. Generally, the Cont 2D with a proper kernel size, padding, and stride itself helps you in both the cases. So work that out. Like these are some sample examples. Transposed convolution is also one very important technique. I'm not going to go in the details of transposed convolutions. I have put in like a very nice article for you people to understand. So that is one good upsampling technique. Now, why do we need all these things? Is because in images, you need to make the network understand that even if you're leaving behind some features in, let's say, downsampling, you should not let the network take away major information from it. So here in transpose convolutions, when you, first of all, when you are moving the filter, you kind of put their values, the overlapping values also inside it, so that you don't lose out on the pixels. And or you kind of upsample the image. So you can read more about this transpose convolution process. Coming on to a part where you would actually be using it in homework 2 part 2. Once you have the image, yeah, this is Bikshaw's image that we found out. So SK image and PIL are like some small techniques of loading an image or opening an image. There are several other libraries. These are just simple examples that we put in front of you that you might want to use. So once you have your image, this portion is something which you would be needing. So we would be using data transformations before we would like to have data transformations before we kind of make it into data set. Now, again, why do we want to do that? Suppose we have this random horizontal flip. There is horizontal flip, there's vertical flip. There are so many types of transformations. This transforms is also inside Torch. You can just go to its library. I'll include the link for it over here. And you can read about several types of transformations. Now, why do we want to do it is the question. The point is that, say you have like the dog image which Rishmi showed, and you want your network to understand better that it can be even, it'll be the same dog that you still need to identify, even if it's in the top position, if it's a rotated position, even if it's in a any type of shape or position that it is, but you still need to identify it. So you need to make the network understand that this is a feature that you need to identify, be it irrespective of where the position is, where the degree of rotation is. So there will be various types of transformations that you might want to apply before putting it into the data sets. This is the folder that you would be loading it from. Sorry about that. And once you have the data set, you would be putting it in the data loader and yeah, just putting it. So this is a basic CNN module that we have presented in front of you, like the layers that we kind of talked about. You can put in various types of layers. You can put in various, you can make a basic block sort of thing where it will be getting repeated in the image extraction, and then put that basic block here. So totally depends on your design network. Here, there are several conv layers, like one conv layer initially has different parameters. The second conv layer has different parameters. So then we have various linear layers also. You can experiment with all of these. You can put batch norm, ReLU, whatever you want, or you might just directly want to use ReLU like this. So yeah, it's just a simple example that we wanted to show you of how you can make your network module. And this is the diagram. So once you have made that module, here's like you can make a model. Now coming on to how you save a model and you load a model, in this particular part of the homework, just make sure that you are definitely saving and loading the model, because there might be cases when you are disconnected in between. But if you have like the entire model state path saved, then you would be able to simply extract it and load it and start either the inference or the training, depending on what you have saved. So you can just simply save it this way and you can just load it, or you can just simply use model.load state date. This is a simple train function that we have given it to you, that you might be needing it in your homework part too. It's a simple where you load your features and your labels, extract the features out of it from the model results, put the criterion, calculate the average loss. And this is an example of how you can save the entire model for your next set of inferences. It's important to save just not the model state dig, but also your optimizer and scheduler when you are saving it, especially when you are going to use this model to run your model again. So like resume training. So that's also one part. Here are some notes about debugging and loading the pre-trained models, which you can just go and read through. Debugging, we are mainly emphasizing via the PDB. PDB is something which I think will eventually, you would start liking it by the end of this course, because you would be needing it everywhere. Print statements are definitely useful, but use PDB more often. You would get a deeper understanding of what's going on. Just a simple notes on debugging the CNNs. And here you have your pre-trained models. You won't be needing mostly a pre-trained model that you would be using. In fact, we won't allow that. But suppose it's just a good to know factor that sometimes if in any of your outside projects in where, or your course project, if you would be needing to use a pre-trained model, how do you use that? How do you load it? And here we have given a simple example for you where you can build the VGG feature extractor. So yeah, pretty much that's it about how you are going to use PyTorch. I'm going to stop sharing. If you have any questions, I can take it now. You can put it in the chat, or you can come to my OH today. Anything.
I need to go back. I clearly messed up one of the GIFs, which Kushal has very rightly indicated in the chat. So I would like to go back and share and like talk a little bit about that. If Mansi is okay, do you want to?
Yeah, go ahead.
let's go back. And we also have a question about filters and how to apply different filters to different parts of images. Okay, we can talk about that. So clearly I messed this up. So what is happening over here is, let's go back. We have this input, which is a blue 4x4 cross size image. We can imagine it has like one channel, and like there are 4 pixels here and 4 pixels of different values here. And the blue highlight that you see, that's the filter that's convolving over the image. So that's why it's moving by a stride of 1 over here. It can also move by a stride of 2, but you know what happens when it moves by a stride of 2? The last column of weights, it will just fall off, or it will go beyond the image, and that's why you need to pad. And as the filter convolves or scans over the entire image, you would get an output, and that output is represented by the green box over here. So that's was one of the clarifications that I had to give. Sorry. Are there any questions about this whole process over here? Otherwise, we can talk about pooling next. Okay, you don't need to be shy, like I'm not a picture over here. Okay, I'm just going to assume that that silence is indicating that people have understood this well. And I hope you do, because if you want to get started, you really need to emphasize on the forward process and think about like how it's happening. Okay, the next part. I know some of the people are talking about pooling. So if it has a different kernel size and at what regions the pooling is applied to. So before we get to that, let's think about this. We talked about weights, which are basically the kernel, right? Like kernel is basically a set of weights. And you are trying to apply the same set of weights to the entire image. Now there comes a concept of shared parameters, which I had not talked about because that's something very complex, and I haven't really gone into the depth of like what and how exactly MLP is scanning over the area and how each MLP contributes to certain number of parameters. And if we take into account this whole MLP structure, yeah, over here, if we take into account all the MLPs, what happens is basically you come up with like 1 billion parameters. So you need to think about shared parameters over here, which I will not try to go in depth into, but there is something like each input layer scans a certain part of the image, and you get that like that weight is basically shared amongst all parameters, sorry, all MLPs. So that's a concept that I would just throw at you, but I won't get into detail because Bhiksha will be covering a lot of these on the Wednesday class. But going back and talking about why exactly are we convolving the same set of kernel or the same set of kernel weights over the entire image. So you want to recognize a certain pattern, right? And you are trying to put the set of weights over this one area. So suppose like the first 3x3 square that you're looking at, and you want to figure out, suppose if there's a flower or not in that area. And based on the pixel values in this region, and here it's 100, just imagine if it wasn't 100, it was like some other like better pixel values, which represents a flower in this first 3x3 square. You convolve the weights, you get the sum product like we talked about, and then you move along and you convolve over the entire image. What happens is once you detect this flower image, you get a higher sum product, right? And that is important because that's where the weights are being applied to the image, and you're trying to find out a specific pattern. So you're trying to find out like a sum product of pixels and see, yeah, so like this sum product resonates with the flower image. Does this appear somewhere else? So that's why you need to move the same filter over the entire image. You could have multiple filters doing it, and that's how like the concept of output channels comes along, because the number of filters that you apply to the same image will be the number of output channels that you come up with in your output size. I hope this makes sense. If it does not, like go to office hours today or talk to me on Monday. We'll try to clear this up more. But if there are any other pressing questions right now, I'm happy to take that. And also Mansi.
Yeah, I can just put one line about the shared parameters basically. So say as Rashmi explained that this is just in case that if you have like if you have the concept of MLP doing the scanning thing, same MLP would not be, we would not be able to use it. So you would be having like different MLPs with different weights, and you would not believe in a very simple network. It ultimately compounds to just using billions of parameters. And I'm not making the figure a billion. We'll put a slide about it on Piazza. But with just a simple convolution, since we are using the same weight filter everywhere to scan it, it just comes down to simple thousands. So the weight of the network, or basically the number of parameters that we are going to use, it reduces like heavily or exponentially from MLPs to simple convolutions.
Okay, so I know there was this one more question about pooling. So let's go and look at pooling. What exactly is pooling? So pooling is another layer. You have a CNN layer that we talked about, like CNN 2D, as Mansi was explaining, right, in the code that PyTorch has. So now you want to apply a pooling, and the reason you apply this pooling layer is basically you have these huge number of parameters in your model, right, and you want to reduce it for reducing the complexity of the model. So you basically, and the choice that of pooling that you have, like average pooling, mean pooling, max pooling, that is basically your decision about the network architecture. Let me iterate that again, because it does not, I would not say like there's a generalized rule about like if there's an image of a dog, you apply a max pooling and you will get better results. There's no rule like that. So like you have to decide, like the way you were trying to decide upon like the width of linear layers, like whether you should apply batch norm or not, whether you should apply dropout or not in your homework 1v2. It's the same case over here. Do you want to apply pooling or not? That's upon you. And if we do use pooling in the baseline architecture of homework 2P2, we'll release a note about that. But going back, let's see what exactly is pooling and how is it like pooling the outputs over here. So this square that you have, this is not your input. Let me clear that again. So this is basically the output that you derive after the filter has convolved over or scanned over the input. And you get all these basic values, okay? Now, the reason there are like colors associated with this square image, and it's important I clarify that, it's not that we are originally or like inherently trying to classify these four belong to a certain group. There's nothing like that. The reason why we applied a color over here is basically to show that we, in a pooling layer, have a 2x2 filter again, or a 2x2 kernel again, and this is convolving above the output of what you get. So this is the output, and you have a filter for the pooling layer, which is convolving, or the kernel, which is convolving. And it's 2x2, so that's why it scans the 2x2 region and it tries to output a value. That's the basic thing. So because it's max over here, we'll take out the max value of the sum product that we get. If it was min, we would have taken the min value. If it was average, then we do we take all the pixel our sum product values and we do an average like we show in the next case over here, and we figure out what exactly the downsampled value is. So I guess like now I hope it makes sense. If it still doesn't, I'll try to post a note on Piazza, reply to that reply to the thread, or like come to office hours. Are there any other questions? I see like the chat box.
Can I just ask a question about submitting homework 1 part 2? When we finish that, do we just zip our code and submit that to AutoGrader, or do we just have to submit the submission to Kaggle and that's all that matters?
So I guess like you have already submitted homework 1P2. I think we talked about this in one of the offices, but yeah, you also submit your code, and that is due 1 week after the on-time deadline. So right now the on-time deadline is on 27th. So after, you still have a week to like clean your code, make it more presentable. You write a small paragraph, I would say, or like 2 paragraphs about like why you chose a certain architecture and what exactly were the hyperparameters that you tuned, and you use that. You take that and you zip up the code with that write-up and you submit it to AutoLab. But that will be due like 1 week after the on-time deadline, and we'll post a note about it. Don't worry.
And it needs to like be able for you guys to run the code as if it like needs to be a proper README and everything?
No, so it's okay if we don't really run the code, but we do look for plagiarism. So even if it's like if it's without a README, but it's a properly formatted code, that's fine. We just need to like run and make sure like your code is not similar to someone else's code.
Thanks.
Mm-hmm. Are there any other questions over here? Okay, I see like Kushal is doing a wonderful job of like answering questions on the chat. Thanks Kushal for joining us and helping us today. If we do not have any other questions, we can just call it a day and have like a 20-minute break to ourselves. We are all sleepy right now. So yeah, last call for questions. And to the people who answered the Harry Potter question, I'll reach out to you. I know your names now. And we can have like 30-minute OH.
I guess I have a general question. How does the complexity and difficulty of this homework compare to the previous one?
Oh, so as the semester progresses, the homeworks become more difficult, very honestly. But the homework 2 P1, it should be less difficult than homework 1 P1, because we realized a lot of people were having problems with AutoGrad. A lot of people had issues with a lot of like node architecture, computational graphs. So like we're trying to dial that difficulty down. For homework 2 P2, it will be a little more complex than homework 1 P2, but don't worry too much about it because we are trying to reduce that complexity as well. So, but it will be a little more complex. That's what I would say.
Yeah,
I have a question.
Yeah, thank you.
Yeah, for homework 1 P2, if I'm getting some score just above 72 and I see a note over there which says this is only evaluated on 30% of the test set. So is it likely to reduce after you complete it on the complete test set?
So it should not, it hardly matters, I would say. So right now, if you're like somewhere above 72, like even slightly more, suppose 72.5, you're good enough. The final, like the final calculation that happens with the 70% data set would eventually just differ by like 0.5% or something. So don't worry, but I would say like for a safe side, keep it at 72.5.
Okay, cool. Thanks.
Yeah, like totally depends if your model is overfitting or not, and the degrees of overfitting. We have seen students where it has decreased a little, like little by actually little, but just be on the safer side.
Yeah, like not significantly. Like you won't see like 72 going to 68. That is not going to happen for sure. That we can guarantee. I'm guessing like